Yes, sir.
Hello, everyone. So, am I audible? Can anyone please tell? Hello.
Hello.
Yeah, am I audible?
Yeah, you are audible, sir.
Okay. Just give me a moment. I'm just setting up. So my screen is visible to all, right?
Okay, sir. It is visible.
Okay, so we'll start. So first of all, I'm Swastik. I am a PMRF or a PhD scholar at IIT Kanpur. And I am a TA for this course, Fundamentals of Electrical Engineering, which is being taught by Professor Debapriya from IIT Kharagpur. So first of all, a very good evening to all of you. We'll start, just a second. So let's start with assignment one. So I hope you all submitted the assignment one. So um, so we'll go through the questions one by one, and if you have doubts, specific doubts, you can ask me, or I'll be solving them. And so then we'll solve them together, right? So yeah. So for the very first question, so did anyone have any questions regarding it, or does someone know how to solve it? People are leaving. Okay. So okay, no worries. So let's solve it. So first of all, what's given in this question is that we have DC loads, right? So there are total 9 lamps of 220 watt each. So the total wattage of the lamps is 180 watts. There are 6 fans. So their wattage comes out to be 420 watts. A television, a refrigerator, okay, sorry, a refrigerator of 140 watts, a refrigerator of 140 watt, AC 1500 watts, and a washing machine. So can anyone tell me what's the next step? Or can anyone do the addition and let me know what's the total load? No? Okay, so we'll do it together. 180, 420, 40, 140, 15, 100, and 800. The total load is 3080 watts, right? And we are given that it's being supplied from a DC mains of 220 volts. So how will we calculate the peak current? Can anyone tell me how can we calculate the peak current? We know the total wattage, we know the voltage of the DC mains. So how can we calculate the current, peak current? I mean, peak current, then it's a DC load. So
wattage by voltage.
yeah, wattage by voltage, correct. So it comes out to be 14, I guess, right? Yeah, 14 amperes. So A is correct. Now let's solve this question. Yeah.
Sir, excuse me, sir.
Yeah.
Is there any scope for doubts clarification regarding assignment 3?
Yeah. I told you, I asked if you have any doubts, we'll proceed with that first.
And you started with assignment 1, that's why I'm asking.
Oh, so you, which assignment are you talking about?
In assignment 3, I have some doubts regarding conceptual doubts are there.
Okay, assignment 3. So yeah, I can discuss some doubts, but yeah, you can tell me what exactly do you need from assignment 1, assignment 3?
In assignment 3, question number 3, we go for question number 3.
Okay, just a second. Let me open the assignment here. Have it open.
Because
Yeah.
these are all, we already solved all these things.
Yeah, you've solved, but I've been told to if there are doubts, I have to proceed with that. But if no one talks, if no one has doubts, I have to solve it full, right? That's why I asked if someone has doubts, please let me know. I can week 3, assignment 3. Okay.
Yes, that is somewhat tough. That's why
Yeah, we'll discuss it first then. Yeah, let me know. So which question are you talking about? Just let me share
I'm
my
talking
screen.
about question number 3, sir. Assignment 3, question number 3.
Okay, so these are jumbled. So if you can just tell me which question to be exact. So for
Is,
me, yeah,
just 1 minute, sir.
I'll share my screen too. Just give me. Yeah, can you see my screen?
Question yes, it is visible, sir. No problem.
Yeah.
Question number
So
3: find the value of resistance R in
yeah.
ohms in figure Q3, such
Yeah.
that the power supplied by the voltage source to the network is same as the power supplied by the current source.
Okay. Yes.
The doubt is can we apply the nodal analysis and mesh analysis simultaneously, sir, for the same circuit?
Just a second. You need to find out R such a way that power supplied by the current source is same as that of the voltage source. So once you apply the voltage, so with the nodal only you will get the answer, I guess.
Nodal only.
Yeah.
I want to know. Now to find the power
So see,
supplied.
tell me one thing. So for the voltage source, what do you require to know how much power it is supplying?
So for voltage source, it is 100 volts.
No,
Current,
no,
so
yeah, you
we should
need
know.
current.
Yeah,
You need
current how, sir?
current over. Yeah, and for the 5 ampere, you need to know current across that 5 ampere source, right? Voltage
Yes.
across the 5 ampere source, right?
Yeah.
If you use only nodal analysis, you'll be able to find it out. I mean, you don't have to go through mesh analysis.
This side, right hand side, 100 volt side, how to find current?
See, I can't tell you the whole question, but see, if you see, there are two nodes, right? One is this node, and the other is
5
this
amperes.
node, right?
Okay.
So once you know the voltages, you can calculate currents too, right? And then once you calculate currents, you know KCL, and then you can calculate the current that is coming out of the 100-volt source as well, right?
Okay.
Yeah, I can only give you certain direction. I can't solve the whole question right now because it's not.
I don't want to solve. I don't want to solve.
Yeah. So if you see, you just need to. So once you get the voltages, because you anyways require voltages across this node, or V1 node, if you call this as one node. So you require V1. Once you get V1 or V2 both, you can then use KCL to calculate the current across that node too. And then from that, equate the powers, and then you will get the resistors. You will get the value of the resistor. That's all. Yeah. That's the only direction I'm going to give to you. So you have to solve it.
Next, please go to fourth one, sir. Fourth one.
Yeah. This one.
Here, 50 volt source is delivering current IS. Yes, IS is delivered by 50 volt source. Fourth one. Now, if I take the first loop current as I1, means I1, then IS and I1 will be same?
Yeah.
Okay, fine.
Because it's the same current going through that mesh, right? So the mesh is I1, and in the same direction there's IS1. So I1 is equal to IS.
Okay, thank you. Next, fifth one. Please give any hint for fifth one.
Okay, so for current to flow, you need a closed circuit, right?
Yeah, that's what.
So that's the only direction I'm going to give to you, because you need a closed circuit for the current to flow. That's it. I mean, because I can't give you, because it's an easy question. If I give you what's required to solve, you won't solve it on your own. I don't want to do that. It's just that for a current to flow, you need a closed circuit, and then you can know you'll know what I'm talking about once you see the question, see the figure.
Okay.
Yeah.
Now I got it.
Any other?
And please explain about power delivered and power absorbed concept, just in 1 or 2 minutes.
Yeah.
Because in some textbooks it is somewhat ambiguity. That's why.
Yeah. Just let me share my screen on my iPad.
Yeah.
That's what I want. It should be a live interaction. It's a live interaction. You can ask your doubt, but if no one asks, I have to solve everything.
That's the problem.
Yeah. So okay. So it's our prerogative what sign convention we have to apply, right?
For power delivered.
Yeah. So for us, the sign convention that this textbook that the instructor is following, it's I guess Alexander Sadiku, right? So in that, plus is given as power absorbed. So power is if it's absorbing, we give it as a plus notation. So that's positive. Yeah. And if it's negative, we say the power is being delivered, right?
Okay. Whether it is source or it is load, sir.
I'm telling you, I'm just telling. So power, if it's being delivered, it's being delivered by a source, right? If it's being absorbed, it's being absorbed by a load. Just hear me out first, okay?
Okay.
Let me tell me this question once. I'll give you this circuit. Just this in my head. So this was discussed in the first week. So I don't have the notes for it now. I'll just do a random circuit and we'll do the analysis together. Yeah. Okay.
Okay.
So these are two resistors, right? Resistor, irrespective of what value it is, it will always consume, right? That you know.
Okay.
So a resistor always absorbs power.
Okay.
Okay. So from the sign convention, if a current is emanating from the positive reference side of the voltage source,
okay,
positive side of the voltage source, it's said to be delivering. So if it's delivering, we say it's negative. The power is if we write power, we write in terms of negative sign, right? But if the yeah, but is someone talking? No.
Yeah,
so yeah. But if the direction is reversed, say 10 ampere is powerful, more powerful, and the current is some I current is flowing to the positive terminal of the voltage source, we say that it's absorbing, right?
Okay.
So and then we say it's a positive with a positive sign. So it's all with reference to how my current I is coming at the positive or the negative side of the terminal. So if it's emanating from the positive side, we say it's delivering, and if it's being fed into that positive side, we say it's we say it's absorbing, right? And same for this case, this current source case. Let's say the voltage comes out to be like this, plus and minus, right?
Okay.
So it's emanating from which side now?
Positive.
The current? Positive side. So what is it doing?
So it's positive means it is
delivering.
Delivering.
Yeah. So it's coming out from the positive terminal of the current source. If I say it's being fed to that positive side,
it is absorbing.
No. I'm sorry. I'm trying. So if I say it's this, so if it's like this, if it's emanating from the positive side or it's coming from the it's coming to the positive terminal of that current source, we say it's absorbing.
Absorbing.
Yeah. Yes. Any other doubt?
No, sir. Very nice.
Yeah. So that's how you denote it. For current source, you check the positive side and the negative terminal of that current source, and for the voltage source, you check from which side the current is emanating, from the positive or the negative.
Okay.
Yeah.
Thank you.
Any other doubt?
No, sir. Thank you very much.
Okay. So anyone else, please, if you have doubts in assignment 1, you can please raise your hand, or you can even unmute yourself. Well, I'll be happy to solve it. Otherwise, I have to go through it fully. Yeah. Anyone? So after this, I'm going to discuss nodal analysis and mesh analysis. So if you want to continue, you can. Anyone? Okay. So how will we solve this question? Question number 3. Can anyone tell me? Anyone? No. So let's solve it then. So what's the equivalent resistance of this whole circuit for this part? So Ka are two resistors in parallel to each other. So what's the equivalent resistance for that? It's Ka by 2 ohms, right? And there's a series resistance too, which is A by K ohms. So the equivalent resistance is K by 2 plus A by K, right? Now, how is power denoted in terms of voltage and... Just a second, sir. Can you... The recordings will be uploaded. Oh, so it would be there in that NPTEL portal, right? I just let me see this one. Yeah, there is this problem solving session, July 2023, in the left hand side column where you see all those week lectures. You'll see there's this Google Sheet link. You can go through that link and you can check all of us. Can you share here? Okay, I share. So why so Sushant doesn't want to attend my class right now. He just wants to see the link later on, right? Yeah, this is the playlist where I upload all of those lectures, so you can go through them one by one. Still in class. No, you're still in class. I mean, you're asking for it, right? Okay. So let's solve this question. So can you tell me what's the power in terms of voltage, which is E, and the equivalent resistance? It's V square by R, right? So it's E square Ka by 2 plus A by K. Now I'm in college classroom. Oh, you're still in class. Oh, okay, no worries. Okay, so how will we solve this question? Can anyone? So now tell me, we need to find the maximum power. So what will we do? Anyone? So I mean, there are only two of you. So if anyone can tell me. So we'll simply do differentiation with respect to K, right? And equate it to 0. That's how we find the maximum um, uh, value of a certain variable. So once we do that, we'll get E square, and then due to differentiation, it would be minus, and then negative squared, and then apply the chain rule, which would be like this. So does anyone have problem with this differentiation? They can let me know if this differentiation is not clear. Okay, so let's take this one to find the value of K. Actually, due to network issue at my place, I couldn't attend the problem solve. So I also want to see the previous 2 weeks problem solving session. Gori, so I have given you the link. They are in the chat box, the playlist link, and they are also there. So there are two more TAs for this course. They also take their classes. One takes from Saturday 5 to 7, and the other takes on Monday 6 to 8. So you can check their links in the NPTEL. So there's this NPTEL problem solving session link on the left hand side of the panel, this window pane, right? And you can check their material as well. So I have updated my link over here in the chat box too. So okay, so for this, what we'll do, we'll equate this to 0, and this would come out to be like this. Since A and A will get cancelled and K square will be equal to 2, that means K is equal to under root 2. Plus minus, so let's say it's plus, right? So the correct answer is C, and that's what's given in the figure as well. So there's this question, since no one is saying, so we'll get to it. So there are 460 watt, 110 volt, but so 460 watt, right? So the total voltage comes out to be 240 volt. They're designed to handle voltage. It's 110 volts. So can we find the resistance from this? We can. So the resistance is nothing but, if we write P in terms of V and R, it's P is equals to V square upon R, right? P is how much? 240. V is 110 square R. So R will come out to be, so it's 50.4167. So we'll write 50.42 ohms, right? So we know the resistance of this part. We know what voltage it's working at, and we know the supply voltage. So we can now easily find R from the voltage divider formula. So what's the voltage divider formula? If we apply it for this R2, so V at R2 is nothing but, if this is Vs, and it's Vs into R2 divided by R plus R2, right? So VR2 is given at 110, Vs is 230, R2 is how much? 50.42, right? So this will come out to be 50.42 plus R, and then we can easily find R, and it come out to be 55 ohms. You can do that. That's how you'll do this question as well, right? So the second question. So Gauri, did you solve this assignment? I mean, you must have. The last date was, I guess, 9th August. Okay, so let's solve it. And there's not many people here. It's because this long weekend, I guess. Okay, so lamp. So the rating of the lamp is what, 40 watts, and it works. If battery is at 100 volt, and calculate the current drawn by the conductance. Okay. So current, how much would be the current? Current is simply what? Wattage upon volt, right? So the current is nothing but 0.4 amps. So that negates two options, A and C. Now we are required to find what's the conductance. So how can we find conductance? Conductance is nothing but I upon B, right? So 0.4 divided by 100, which is what? 4 millimhos. So the answer is B. Okay, so this is a very good question. So we are given current, and we are given the waveform of current varying with time, right? So we know how we can write charge in terms of I in time. Q is nothing but I dt. So what exactly does this say about this waveform? That Q is nothing but the area under the curve of this current varying with time, right? So let's solve. What is this this area? This area is nothing but half into 12 into 2, right? So this is 12. How much is this area? This is a square, right? Is it a square? 2, 4. No, it's a rectangle. So what is this area? It's 12 into 2, right? 24. Now we are required to find this area. So we'll divide it. There's this rectangle part, and there's this triangle and a rectangle part, right? So the triangle part is nothing but, it's going from 12 to 30. This is 18. And the breadth is 2. So half into 18. So 18 plus 24, right? And this is also a rectangle. So this is what? 3 into 30, 90. And this is a triangle. This is half into 30 into 1, which is 15. So if we can add all of this together, what does it come out to be? 24 plus 18 plus 24 plus 19 plus 15. It comes out to be 183, right? And that's the correct answer. Okay. So this battery charger, it supplies a constant current into a 200 volt battery for 2 hours, right? So it's applying, time is given as 2 hours. What voltage is of battery? 200 volts. Okay. And for the whole time, energy is 4 kilowatt hour. So what is the power? Power is nothing but E by T, and this comes out to be 2 kilowatt, right? And then current is simply, we know P is equal to VI. I is equals to nothing but 2000 watt divided by 200 volts. This is nothing but 10 ampere. Okay. Okay, let's solve this question. So we are given a load line of the source. So a load line is given as I plus V is equals to 50. So therefore I is nothing but 50 minus V, right? And we know the current through the resistance is also I. Now, and the voltage across the resistor from the Ohm's law, we'll use Ohm's law. We'll get V is equals to IR. Now I is what? 50 minus V, right? So V is equals to 50 minus. Let's do it like this, right? 50 minus I is equals to IR. 50 is equals to IR plus 1. I is nothing but 50 upon R plus 1, which is how much? R is given as 4. So I is nothing but 10 amperes. This question. So can anyone, who was asking me doubts? Is that she is left. Determine the amount of power delivered or absorbed by the dependent source. Can anyone solve this question? Gauri, can you solve this question? I mean, you're the only one here. No. Okay, let's solve it then. So the power delivered by or absorbed by this dependent source. So let's see. So power delivered or absorbed by this dependent source is nothing but into I, right? So which comes out to be 3I square. Right. So how will we find this I? So we can use KVL, right? So it's 40 minus 9I minus 3I minus 16 equals to 0. 24, 12I. I is what? 2 amperes. Therefore, P of 3I is nothing but 3 into 2 square. 12. So 12 watt absorbed, right? Good. Okay, this 9th question. So total load is how much? So the total load is nothing but, so 6 into 20 for lamps, and then 70 into 4 for fans, 10 into 200 for computers, two into 50 for printers, 2 into 1500 for earphones. So Gauri, can you tell me what's the total load if you add all of it? Yeah. So total load is 5500. I'm going by what you are writing. I haven't calculated. So 5500 watt, right? So now it's saying that for an average period, it's working 60%, right? So can you tell me what's the total energy consumed for the whole June? So it's saying that for a day, it's only consuming 60% of the total load, right? So from that, can you tell me how many? So there are total of 30 days. So I've made it easier for you. So can you tell me the total energy consumed for June? Yeah, it's 3300 kWh, right? Okay. It's 3300 kilowatt hour. Can you check if it's correct? I think it's not correct. Total energy, I'm talking about the total energy. Okay, let's do it. So it's nothing but 60% of 5500 multiplied by 24 hours in a day, and then total of 30 days, right? So this comes out to be, so are you calculating? No. 60. Just a second. Is this 5500? 2376. Oh, yeah. So how much are you getting in kWh? Can you tell me? So from my calculation, I'm getting 2376 kilowatt hours, right? So units are generally measured. So the business, so the electricity is generally measured. Energy is generally measured in kilowatt hours, right? So that's why I wrote this in kilowatt hours. So you can just write into 10 raised to power minus 3 to make sure it's in kilowatt hours. So now we know there's this fixed charge. What's the fixed charge? Fixed charge of rupees 100, right? Now for the first 600 units, so first 600 units, it's charging at 3 rupees. So that means a total of 1800, right? And how many units left? 1776 units are left. And for the next, I guess, 800 units, it's charging 4 rupees. So that means it's 3200. So how many left? 976 units left, right? And the rest of it are being charged at 5 rupees. 5 rupees, right? How much is this? 4880. So can you sum it up? For me, it's coming out to be 9980 rupees, which falls in D. Okay. So, can you tell me what are linear networks and what are non-linear networks? So, a linear network is nothing but the one that follows Ohm's law linearly, right? And there's no variation with variation or changes with respect to time or with respect to time. So, it follows Ohm's law. Here, a non-linear network doesn't follow Ohm's law. But since the Kirchhoff's laws are based on what? They are based on law of conservation of energy and charges, right? So they are based on law of conservation of energy and charges, right? And law of conservation of charge or energy can hold true for both linear or non-linear networks. So the first equation is the first assertion is wrong, right? Okay. Second, they've written the Ohm's law is applicable only to the lumped elements. So what are lumped and so one is lumped and the other is distributed elements. Can you tell me what's lumped elements and what's distributed elements? Just a second. Can anyone tell me what's it's only Gori. So can you tell me what's lumped and distributed elements? Okay, so lumped elements are those which don't have a variation with respect to the length of circuitry. You can say the length of the circuitry, they don't vary with respect to the length of circuitry, right? They show variation with respect to right. Now, what exactly is Ohm's law? Ohm's law states that if temperature is held constant, voltages vary linearly with current, right? So we can't judge based on how if they are lumped or if they are distributed. Ohm's law can't be applicable. They can be applicable, right? Because they're not varying with respect to, so they don't violate the basic condition of the Ohm's law. So hence this assertion is also wrong. Now the third one, Ohm's law is valid only at constant temperature. This is true. Why? We treat the proportionality constant of this equation as resistance, right? V equals to IRP, right? And we say that this is true only at constant temperature. Why? Because if temperature changes, R changes with temperature. So I don't recall. I'm not unable to recall the exact, but I guess it's R1 plus alpha delta T is how they vary, right? I don't recall it fully, but that's how it varies. It varies with temperature, right? So hence Ohm's law is valid only at a constant temperature. So this equation, this one is true. Hence the correct option is D, which is 3 only, because only the third inference is true. Okay, this is what assignment 1 was. So assignment 2, I'm not going to delve into further. You can watch other people, other TAs work as well. So what I want to discuss is week 3. So week 3, you saw discussions related to 2 very new concepts called nodal analysis and mesh analysis, right? So we'll start with nodal analysis. So what is a node? So we did talk about it in the last lecture. A node is nothing but a node is nothing but a terminal at which any element that can be connected, right? For example, if I draw this circuitry, how many nodes are there? This is a node. Since these 2 nodes are connected to each other, are these 2 nodes connected to each other? And these 2 nodes are connected to each other. This is also a node. So this is 1 node, and this is the 3rd node, and this is 4th node. So there are, in totality, there are 4 nodes, but we won't denote them as a single node. We'll say that this is also a node. This is 1. I'll tell you why these are a single nodes. Bear with me for a moment. Right, B1, B2. So these are what nodes. So this is what nodes are. So in nodal analysis, what you do, you just want to, you just solve them systematically using KCL, Kirchhoff's current law, right? And what is Kirchhoff's current law? Nothing but current entering a node is equal to current leaving a node, which is based on the fact that charge can neither be created nor be destroyed. It can only travel from one place to the other. And hence, from that law of conservation of charge, this law is derived, right? So let's draw a circuit and I'll tell. And so let's consider the circuit only. Let me write. So what is the main aim we require from nodes? We'll do V1 or just V R1 R3. So in KCL, we can get voltages at all the nodes and the current, which is, so we can derive voltages from all the nodes, and then from that, we can derive the currents from entering in each of the branches connected to those nodes, right? So first of all, what we require, so let's steps to apply nodal analysis. So what are the steps? So the first step is to figure out a reference node, right? So what you require is a reference node. So just if you can, yeah. So what you require is a reference node, right? So what is a reference node? You just pick one node and then term it to be. These are also connected to similar points. This is also. Right. So you just connect a reference or a ground to that node, and you term it as a zero node, zeroth node. So this is a zeroth node. This is also zeroth node, and this is also zeroth node because they are connected to the same nodes, right? Same potentials. So since they are at the same potential, all of these are zeroth nodes. Okay. So now you've got the reference node, and now for the non-reference nodes, you figure out, you write the voltages at those you want to figure out the voltages at those non-reference nodes. So let's term this node as V1 and the voltage across this node as V1. Now, since these two nodes are connected to each other, the voltages at both of these nodes are same. That's why I took them as a single node. So we can write V2 and V2 here as well. So it won't matter. So that's how, so what is the step? First of all, figure out a reference node and write voltage notations at all non-reference nodes. Very good. And now from those non-reference nodes, what we require is we want to use KCL Once you use KCL at all of the non-reference nodes, you will get n-1 simultaneous equations. And you can use solvers, or you can solve it by hand too, using Kramer's rule and other stuff, which is taught by Debapriya sir. And then you can find the solution for all the voltages at all of those nodes. You can also use a scientific calculator. There's this equation option over there where you can add all of those A matrix and B matrix, and you can find get the final values for all of those nodes. And you can also use matrix calculators, which are available online. But since it's I don't know, the final exam is going to be if it's going to allow scientific calculators, which I hope it should. So you can always use the scientific calculators to find the solutions to those. So let's do one question. First of all, before moving on to question. So anyone who has a doubt can let me know if they have a doubt in nodal analysis. Anyone? And good question to solve. No one has doubts? Okay. So let's solve one question. Sample problem. So first we'll look at only current sources connected to current sources connected on the branches of the nodes. So let's look at this question. This is given in the exercise, so we can use that too. So here you'll see in two branches there are two current sources connected, one 1 ampere one and the other a 4 ampere one, right? So we need to find V1 and V2 for the circuit using nodal equations, right? Nodal analysis. So we can do that. So let's apply case. So let's first of all figure out the reference node. They have already given us the reference node. This is the reference node, and all of these nodes are at a reference. So these are at 0th volt, right? And yeah. So let's apply KCL at And they have also, so first step is done, and for the second step we need to write notations at all of those nodes, which also they have given us. So now we have to use KCL at all of those nodes. Let's do it at 1. So what would it be? It would be V1 minus V0, which is at 0. So it would be V1 by 6 plus V1 minus V2. Oh, let's not do it like this. Let's write the currents. So this is what I1, this is I2, and this is I3. So what is KCL? KCL would come out to be I1 equals to I2 plus I3, right? So what is I1? I1 is nothing but 1. I2 is V1 minus 0 upon 2 plus I3 is V1 minus V2 by 6, right? So this is first equation. Similarly, for the second node, I3 is coming this way. This is I4 and this is I5. So what is the right? So what would be the KCL? KCL would be I3 equal to I4 plus I5, which would come out to be how much? V1 minus V2 by 6 equals to V2 by 7 plus 4 ampere, right? So this is equation second. We can rewrite equation 1. So equation 1 is nothing but 6V1 or 8V1 minus 2V2 equal to 12, right? And the second equation, what would it be? It would be 7V1 minus 13V2 equal to 4. Is that correct? 24, right? No, it would be 4 into 7 into 6. So how much? So let's solve this using calculators. So Bori, can you find the answer as well? We'll cross check. You can write this in the matrix form as well. It would be 8 minus 2, 7 minus 13, V1, V2 equals to 12, 168. You can use matrix inversion, Kramer's rule, substitution, equation solvers online, anything, and you can get the answer. Just let me know if you're doing, Gori. So V1 is minus 2 volt for me, and V2 is minus 14 volt. Okay, and that's that corresponds to the answers in the exercise as well. So Keith, since you recently joined, what I was doing before people left, it's nodal analysis and mesh analysis. So I told how to apply nodal analysis, and then I solved one question on nodal analysis, right? Now we'll do one question with a voltage source. So first of all, we require to place a reference node, which is already been done for us. So all of these nodes are at reference potential, which is 0 volts. And we then have to write notations of the non-reference volts, which is also done for us, V1 and V2. Now we need to apply KCL or KCL at all of these non-reference nodes. So KCL at node 1, what would it be? KCL at node 1 would be so this is one current coming, I2, I3. It will be nothing but I1 equal to I2 plus I3, right? Now, since the 100 volt is connected directly across to this branch, which is the 25 ohm branch, and the voltage V1, how much would it be? It would be nothing but 100 volts, right? Is this correct? So we don't even need to write KCL at that node 1 because the voltage is already given. So now at node 2, what is it going to be? So I3 is coming, 5 ampere is coming, and I4 is moving out. So this is how we'll write, which is nothing but V1 minus V2 by 10 plus 5 equals to V2 by 50. V1 is 100. 100 minus V2 by 10 plus 5 equals to V2 by 50. So we can just simply solve it for V2. How much would it be? 500 minus 5 V2 plus 250 equals to V2. So this is nothing but 750 divided by 6. So V2 would come out to be 125 volt. Now there's this concept of supernode. So what is a supernode? Can anyone tell me what is a supernode? No. Okay, let's go. So we have, let's say, a circuit like this. So if we write nodes, how many nodes are there? There are a total of 3 nodes. First, we'll do the reference node. This would be our reference node. So that means all of these nodes are at 0% potential. This is the first node. This would be a bit. Let's do it discreetly. We'll use capital V1 and capital V2 for this. And this is V2 and this is V3. Now, if between two non-reference nodes a voltage source is connected, we term that as a supernode. So this is a supernode since it's connected between two non-reference nodes, right? So, yeah. So what do we do with this supernode? So in a supernode, we just, so if we solve this, it's better if we solve it using an example, right? But yeah, let's continue with what we are doing, right? So what we can do is we know simply that V3 is nothing but capital V2 volts because it's connected directly at that terminal. And for this supernode, what we need is we need to apply KCL and KVL simultaneously. So at supernode, we need to apply KCL and KVL simultaneously to solve it, right? So how exactly are we going to do that, right? So let's apply KCL. I3, let's I2, and then this is I1, I3, I2, and I4, right? So for a supernode, if this is a supernode, we'll collectively call it as a single node. So for this supernode, what we want is we want to check how many how much current is entering to that supernode and how much is leaving, right? So I1 and I3 KCL so I1 and I4 are leaving and I2 and I3 are entering that supernode, right? So that's how we write this supernode. So what exactly is I1? I1 is nothing but V1 upon R1, right? I4 is nothing but V2 upon R2. I2 is V3 minus V2 by R3, and I3 is V3 minus V1 by R4, right? That's precisely what it is. And now what we'll do is we'll apply, rewrite these steps. All right, just now we'll apply KVL at that supernode. So how do we apply KVL? We know this supernode. Let's rewrite it. It's like this, right? This is V1, this is V2, this is capital V1, this is R1, this is R2, and this is connected to reference. So let's apply KVL. So we know this potential is how much? V1. This potential is V2. So it's V1 plus capital V1 minus small v2 equal to 0. That's what exactly would be our KVL. So V1 minus V2 is equal to capital V1. So from these, so we applied KVL, right? And from this, we can directly find out the relation. So since V3 is known, right? And the only unknowns are V1 and V2, right? V3 is known. So two equations and there are two variables. These two equations. And there are two variables. and we can easily find out what's the value of the smaller v1 and v2 at both of those nodes. So what exactly are our steps at this supernode? So we apply KCL and KVL simultaneously. Let's mention some properties of this supernode. So the first property is that we require to apply KCL and KVL simultaneously. Right. Second, it does not have a voltage of its own, right? What exactly do I mean by this statement? This statement means that V1 and V2 are what? So basically the capital V1 is just the difference between the voltages at the two nodes, right? It does not have a voltage of its own. It's just that the two nodal voltages, the difference between the two nodal voltages is what is equal to that voltage between those two nodes, right? And third, a voltage source provides directly the constraint exactly. Since I got this V1, the difference between those two nodes, nodal voltages is equal to the voltage source, right? Voltage of the voltage source. Once I get this, getting the values of V1 and V2 from the other equation is quite easy, because because we have two equations and two variables, and we can always solve it. Now, even though there's this concept of supernode, it's just there to simplify the solving of your circuit, right? But you can also use the nodal analysis on all of those nodes. Don't take it as a super node. Even if you do that, you'll come up with this equation only, because all of those would cancel out to become this one equation. So even if you do that, the outcome would be this only. So if you don't seem to remember how to solve that super node, no worries. Just solve it like how you solve the ordinary nodes. You'll get the answers from that as well. But it's better to know this. It comes handy, and it's speedy in a way, right? So let's solve one question now. Let me see if I have a photograph for that. I will take I don't have a question. Yeah. So using our knowledge of that supernode, let's solve this equation now. So let's solve this now. Sorry. So reference node is already given there. All of this is 0, right? Now V1 and V2 notations of the non-reference nodes is also done. Now, since between two non-reference node a voltage source is connected over here, this here right here is our super node, right? So what exactly do we need to do to solve this circuit? Apply KCL and KVL simultaneously, right? So let's apply KCL. So there's this current, it's not visible, right? I1, I2, I3, and I4 is given. Let's apply KCL at super node. So which current is entering? 5. Let's denote this as unstable. So 5 plus I2 is equals to I1 plus I3 plus 10, right? Okay. So what exactly is, so let's rewrite this. It would be I2 minus I1 minus I3 is equal to 5. What is I2? I2 is V2 minus V1 by 8 minus what is I1? I1 is V1 by 2. What is V2? No, that's V2 by 4 equals to 5, right? And now apply KVL as well. So V1 minus V2 is equal to, sorry. So V1 plus 2 minus V2 is equal to 0. So that means V2 minus V1 equals to 2. Right? Two equations, two variables. Let's rewrite the first equation, simplify first. From 1, this is 8 V2 minus V1 minus, which comes out to be, let's solve it using a calculator. So V2 comes out to be minus 5 volt. And V1 comes out to be minus 7 volt. Right? Let me see if this is correct. Minus 5.33. So there must be some calculation error. Let me see. V2 minus V1 by 8 minus V1 by 2 minus V2 by 4 equal to 5, right? Oh yeah. I did a blunder on. This won't be here because this is a super node, right? So the current entering is 5 ampere and leaving is I1, I3, and I4. Right? So V1 by 2. So this would be V1 equals to 10. That's good. We solve this. Minus 5.33 and minus 1. Yeah. So that's exactly how you solve this full circuit. Okay. Now I want to discuss mesh analysis as well. Okay, just remember that when you remove this node, you don't have to take this current. I'm sorry I took that because I wrote it once, so I forgot not writing it. So basically, this is connected into the same circuit. So it's just 5 ampere entering, and I2 and I3 would leave that circuit, that super node. So once that's done, you apply KCL, you'll get this circuit. Yeah, you'll get this circuit, and then you can solve these two equations to find out what is the value of V2 and V1. So let's do mesh analysis. So mesh analysis, you require two concepts. One is what is a loop, and the second is what is a mesh. So there's a difference between these two terms. So it's not major difference, but it's a considerable difference once you do the analysis. So you'll know why it's called mesh analysis and why not loop analysis. So what exactly is it? It's take a circuit, for example. Right. So if I write these A, B, C. So what exactly would a loop be? A loop could be A, B, C, F, A. It could also be B, C, D, E, B. And it can also be A, B, C, D, E, F, A, right? But for mesh, there's a difference. A mesh can't consist, so for a mesh, there can't be another loop inside that mesh, right? So you can see for that A, B, C, D, E, F, A, there are two meshes. One is A, there are two other loops too, which is A, B, C, F, A, B, E, F, A, and the other is B, C, D, E, B, right? So, so that's what a loop is. A loop can have other loops inside that loop too. For example, A, B, C, D, E, F, A here, this whole circuitry. But a mesh, it can't have. So what that means, this is a mesh and this is also a mesh. So there's a difference between these two terms, and that's why it's called a mesh analysis rather than loop analysis. Now, let's see what exactly and how, where is it applicable? So it's applicable only to planar circuits. So what do I mean by planar? So in a planar circuit, two branches must not cut each other at any given at any node at any two different nodes. In a non-planar, it can happen, but not in a planar. So if for a planar, it should be a 2D circuit. Now, if there is a non-planar circuit which you can convert to a planar, very good. You can apply mesh analysis over there. But if it can't be converted to a planar circuit, you can't apply mesh analysis over there. So it's only applicable to planar circuit. That's one thing. And how much time? It's 5:30, right? Okay. So let's solve a problem, sample problem to. Let's do one thing. Let's solve the first problem using which we solved using node analysis. Solving a problem would be a better way to okay. So since there's only Nagesh over here, and if he doesn't mind unmuting himself, can he tell me what is a node, what is a loop, in how many loops are there and how many meshes are there? Okay, nodes. So there are three meshes, right? So let's write the values for all of those meshes. So this is one mesh, this is the second mesh, and this is the third mesh. Let us call this as I1, this is I2, and this is I3, right? So what we do, we apply KVL here. For nodal analysis, you applied KCL all of these nodes. Now for all of these meshes, you require to write KVL. So for first mesh, what is KVL? Now there's a concept. So before moving there, let's tell you a concept. So there's this concept of what is it called? Super mesh, right? So what is a super mesh? So can Nagesh tell me what is a super mesh? No. Oh, sorry. I should be here. Can you tell me what is a super mesh? So a super node we had between two different nodes. There was this voltage was connected in between. So it rendered that as a super node. So what we did, we took all of those currents entering that node. The super node was considered to be a single node, and we used all of those currents entering that node and coming out of that, we equated them to each other. That is applied KCL and KVL simultaneously and got the results for it. Now for the super mesh, we have a, a, a current source connected directly at the connected as a branch. So here, this is connected. This is one current source and this is the second current source, right? So that means we can directly call this I1 as what? So we can even remove this this elements. So what we do is we remove what do we do? So once we remove, there's no, so there won't be one, there won't be this, if we remove this won't be a mesh and this won't be a mesh. Let's apply mesh analysis to the second node. Sorry, second mesh. So what would it be? It would be plus minus, plus minus, plus minus. So it would be 2 I2 minus I1, sorry. And then 6 I2, 7 I2 minus I3. So can you tell me what is I1 now, Nagesh? Okay. So I1 is what? 1 ampere, because it's this current, right? This current is what? It's 1 ampere only. That's what this mesh is talking about. And this current I3 is what? 4 amperes only. So, and I3 is 4 ampere. And from that, we can directly find out what I2 is. Right? So we can solve this and we can easily find out I2. So it will come out to be -2. So I2 would come out to be 2 amperes. And from that, you can easily kind of find out what V1 would be, right? Now, this done. Let's find out what V1 is. So what would be V1? So V1 is nothing but 2 into I1 minus I2. Now I1 is what? 1 ampere. I2 is 2 ampere. This comes out to be -2 volts. And what is V2? V2 is nothing but 7 I2 minus I3. Right? So this is what? 7, 2 minus 4, which is what? -14 volts. Right? So that's how you can solve this problem using both nodal analysis. I solved this problem using both nodal analysis and mesh analysis. Now you must have this question in mind: where to apply which one? Like where can you apply nodal analysis and where can you apply mesh analysis? So first of all, you should always try to minimize the number of simultaneous equations you should minimize the amount of equations you get from solving those by using any of these methods. Why? Because the more equations you have, the lengthier it would get, or the lengthier it would be for you to solve that equations. Right? Now, if you need to find voltages at node, always use nodal analysis. It's because by solving nodal analysis, you directly get the nodal voltage. For currents, you use mesh analysis because you can then directly find out the mesh currents, right? Now what else? Where else can you use where else can you find the reason to use which kind of analysis? For voltages, the number of I guess this is it. I can only think of these three reasons. So, and one more thing, if you think that solving something is easier for you, even if the number of equations are more, go ahead with that. But try it. But then the hardness of the problem is associated with the number of equations you have. So try and minimize the number of equations, and the complexity of the problem would also reduce. So that's how you solve this. This using both. So today we discussed assignment 1, and then we discussed nodal analysis. In nodal analysis, what do you use? You use KCL at all of those nodes, and then come up with the nodal voltages at all of those nodes, that all of the non-reference nodes. Of course, for this, first you need to realize which is the datum or the reference node. Always find out the datum or the reference node, and then solve the problem next. So then I acquainted you with the concept of supernode. A supernode is nothing but in which between two non-reference nodes, a voltage source is connected, right? So once you identify a supernode, the life becomes easier for you, because then you don't have to, you don't have to solve the equations fully, because you can just try and minimize the number of, because you can try and minimize the number of equations you have. At a supernode, you have to apply KCL and KVL simultaneously. Like for example, here there is a voltage source capital V1 connected between two non-reference nodes, small V1 and V2. So you apply KCL, you see I3, I1, so I3 and I2 are currents entering the circuit, and I1 and I4 are leaving. So use those, and then you calculate what are the different, and then you use those to find out, to get an equation, and then you also use the KVL at that supernode. So once you use that, you'll find that it's nothing but difference between those two nodal voltages is equal to the voltage in between those nodes. So once you do that, the life becomes easier for you. You can just simply solve these two equations, because there are two equations and two variables, and then you can find out the answers. Like for example, here we solved this concept using supernode, where you had a 2-volt source connected between V1 and V2. So here, this whole node is a supernode, right? Supernode. And the currents entering it is only the 5 ampere current, and leaving are I1, I3, and 10 ampere. So you use that, and then create an equation, and then apply KVL at that node as well. KVL would be over here, and then you'll get this equation V2 minus V1 equals to 2. Solve those two equations, and then you will get the answers. Then we went ahead, and then we talked about mesh analysis. We first identified how to identify a loop, and then we tried identifying how to identify a mesh. And then I solved a sample problem, which was the first sample problem only, and using a mesh analysis. And then we got to know that using both the methods, we can get the same answers. Using which methods depends on what you are required to find, and second, the amount of complexity. If you feel using mesh analysis is less complex, you feel free to do so. But if you feel that using nodal analysis is not that complex, feel free to do that as well. Just remember that thing, use the one in which number of equations are less, so that life is easier for you. So that's all. If anyone has any questions, Nagesh, you're the only one here. If you have questions, you can let me know. Yeah, any questions? No. Okay, so we'll see you next Saturday. Okay, bye-bye, take care. Yeah. Can you leave the meeting? I have to close it.